I'm Charles Alcock. I'm the director of the CFA. I think most of the people on this Zoom session know me or know of me. And this is the clay lecture that we're about to get started. And I'll start by talking a little bit about the clay family and their support for mathematics and astronomy. Landon Clay was an investor who was very generous with intellectual pursuits. He established the Clay Mathematics Institute and the Clay Mathematics Prize, which is a very well-known prize in that field. But of course, of much more direct interest to us, he took an interest in astronomy, and he supported our participation in the second of the Magellan telescopes, which is known as the Clay Telescope at Las Campanas in Chile. And a little less than 20 years ago, inaugurated the first of the Clay Fellowships. And just of note, that first Clay Fellow is Vicky Calagera, who's now on the faculty at Northwestern. And we had the pleasure of welcoming her to the National Academy of Sciences last year. So it's also less well known that the very first philanthropic gift in support of the Giant Magellan Telescope was made by the Clay family to SAO. It was towards the construction and the development of the first mirror segment for the Giant Magellan Telescope. And there was a significant technological issue as to whether those mirrors could be successfully polished. And this Clay gift actually very much helped that get started. So sadly, Landon passed away in 2017, but we're joined today by his son, Thomas, who's very generously representing the family in these matters. And he's also recently joined the Smithsonian Astrophysical Observatory Advisory Board, which I've been trying to get him to join for some considerable time. So I view that as a success. So I'll pass the mic virtually over to Thomas, who I think wants to say a few things.
Certainly, and thank you, Charles, and hello to everyone. And I'll just share just a couple thoughts as we get started here. It certainly was one of the great pleasures of the last couple of decades of my father's life to see, to be part of the sorts of scientific programs that Charles mentioned here, and the telescopes and in particular trying to, what he most enjoyed was trying to support critical early moments, whether that's in a scientific project or in an academic's career, and he truly enjoyed these lectures. He was, I can't say for sure, but I think he attended the vast majority of them in person. And as I started working with him, I got to see just how much energy he got from these lectures every year, every spring, and it was one of the great regrets when I moved away from Boston and Cambridge 3 years ago that we weren't able to continue attending these. So one of the small upsides of all of us having to do these things remotely this year is that I'm very glad to be able to participate this year and watch Sirio in person as the lecture takes place. So. My family has really enjoyed our association with the Institute for a great many years, and we're delighted to be here for today's talk. So thank you very much. I'll hand it back over to Charles.
Okay, thank you, Thomas. And it's a pleasure to have you join us this afternoon. So let's get to it. Our speaker today is Dr. Sirio Belli. He's a native of Italy, who was educated for undergraduate studies at the University of Bologna. And then he went to Caltech for his graduate studies, where he worked with Richard Ellis. Upon completing his graduate studies, he went to the Max Planck Institute for Extraterrestrial Physics, as most of you know, is just outside Munich in Germany, as a postdoc. And then he joined us in 2019 as a Clay Fellow. And Sirio is going to talk to us today about his work on the very high redshift universe, specifically galaxy quenching in the high redshift universe. So Sirio, it's all up to you now.
Thank you. Right, so I'm going to show some of the work I've been doing over the last few years, and I'm very excited to show some of the recent work I've been doing in the last year since I joined the CFA. And my work deals with the problem of how galaxies turn off their star formation. This is called galaxy quenching, and particularly how high-redshift galaxies do so in the early universe. And I think that the motivation for this sort of work is very simple. When we look at these beautiful Hubble Space Telescope deep images, the first thing we notice is the variety of galaxies. We see different colors and different shapes. And I remember when I started studying galaxies as an undergrad, I was a bit frustrated at the fact that I couldn't find a simple explanation that would really make me understand why there are spiral galaxies that are gas-rich and have very young stars, and ellipticals that, on the other hand, are passive and have old stars and don't have any gas. And I thought that my textbooks and my teachers weren't doing a good job. And then in grad school, I actually remember realizing at some point that actually no one knows. This is one of the most important open questions in the field. And it's amazing that we're still asking this question, which is really one of the most basic ones you can ask when you look at galaxies. And this really goes back almost a century to Edwin Hubble, who, after discovering galaxies basically and measuring their distances and understanding that these were systems outside of the Milky Way, he started the first categorization of galaxies. And he did it by morphology, which was the simplest thing you could do at the time. So he made this famous tuning fork diagram where we have ellipticals and S0 or lenticular galaxies that form a sequence, and he called these the early type galaxies. And on the other hand, we have the spiral galaxies, which he called late type. And he did have a simple formation scenario in mind where early type galaxies represent the early stage where stars and gas are collapsing and eventually forming spiral galaxies. That's why he named them early and late types, and we still use these names, although we now know that that's definitely not what happens in the universe, because spiral galaxies are younger than ellipticals, so they can't be the descendants. Now, in modern times, we have a different way of looking at this, and we call this galaxy bimodality, which is just a simple way to say that there are essentially two types of galaxies. And we can look at the kinematics, where we would call the ellipticals slow rotators and the spirals fast rotators. And this is connected to the angular momentum, so it's a more physical classification. But perhaps the most famous type of bimodality is the one in color. And this became very clear about 20 years ago with the Sloan Digital Sky Survey, when for the first time we had a very large sample, volume-limited sample of galaxies. And if you plot the histogram for any color, such as U minus R, you clearly see these two peaks. So you see that galaxies are either red or blue. Now, because dust can make young galaxies look red, today we tend to use two colors instead of just one. And the most common choice is U minus V and V minus J. So this is the so-called UVJ diagram, which I will show often today. And these are reference colors, so it doesn't matter what redshift you're looking at, you're still looking at the same intrinsic properties of galaxies. And in this diagram, you see that we have two very clearly distinct peaks. We have blue galaxies down here and red old galaxies up here, where now we're removing the confounding factor of dust attenuation. So many people just looking at these diagrams would think, well, clearly we need quenching, which is an event that turns off star formation in blue galaxies and makes them red, because we don't have a lot of intermediate galaxies. We have to be very careful, though, because stellar evolution is complex and nonlinear, so that an older population will eventually reach a saturation in color. It won't get much redder after some time, and you can actually naturally produce this secondary peak, even without having a true bimodality in the underlying star formation rate distribution, for example. So the real motivation for galaxy quenching as some mechanism that we need to study is really theoretical. And it is the link between the observed universe one hand, where we have galaxies, and the lambda CDM universe, where we have only dark matter halos. So to connect these two universes, we need quenching. First of all, because if you look at the numbers of galaxies as a function of their mass, the blue line here is the observed distribution, you find a very steep fall off. So massive galaxies don't grow after a certain mass. But if you look at the number of dark matter halos in these simulations from lambda CDM, you find a simple power law. So the fact that these massive galaxies must stop their growth is what we call quenching. And by the way, today I'm only talking about massive galaxies. There is also what is something called environmental quenching, which affects satellites, and it's due to completely different physical mechanisms, and I will not talk about that today. Another important aspect here is that we also need quenching to break the hierarchical structure formation that is intrinsic in lambda CDM. This means that when you look at dark matter halos, the most massive halos are the ones that form last because they assemble from smaller halos. But observed galaxies have the opposite trend. They are anti-hierarchical. And this is one of the main results of local studies of galaxy archaeology. You can see in this cartoon here from a famous study that more massive galaxies have a range of stellar ages that is narrower, so they form rapidly, and it's also older, so they form in the early universe. So the most massive galaxies are older instead of being younger. Now, if you are an observer like me, there is also a better way to look at this, in my view, that doesn't require you to follow all the lambda CDM formalism and predictions. And this is asking a very simple question, which is, well, aren't galaxies simply running out of gas so that, starting with some amount of gas, you form stars and you're blue and spirals, and then you run out and you become passive and quiescent? Well, we can ask this question, and then we can go out and measure properties for galaxies in the real universe. In particular, we can measure the molecular gas mass. And this is really important because the molecular gas, the cold gas, is the fuel for star formation. And we can also measure the star formation rate. And if you take the ratio of these two quantities, that's called the depletion time. And that is simply the time it takes to deplete the reservoir of gas if you keep the star formation rate constant. And if you measure this quantity for real galaxies, you find roughly 1 gigayear. It does change with redshift by a factor of 2, but let's say 1 gigayear is a good order of magnitude measurement. And now we observe star-forming galaxies at high and low redshift. And we know that some of these star-forming galaxies kept forming stars for the whole age of the universe, which is an order of magnitude larger than this depletion time. And the only way you can do that is if you replenish the gas reservoir. And that's why you definitely do need to consider the cosmological environment. We know that for star-forming galaxies, there is a rather complex gas cycle with inflows from filaments into the halo. The gas in the halo is hot, it needs to cool. And then once you have cold gas, you can form stars, and you can also remove gas with outflows. So now the question really is the other way around, right? What can you do to stop this gas cycle so that the galaxy becomes quiescent? And now, unfortunately, you can do a lot of things. Theorists are very creative, and they came up with a very long list of possible processes. And here I tried to just summarize the main families of these processes. Each individual mechanism can be due to things like AGN feedback, so supermassive black holes, or cosmological effects, or gravitational effects, and so on. But basically, you can split this into 5 different families. You can do something to the inflow. You can prevent the cooling. You can have cold gas that doesn't form stars, so you suppress the ability to form stars because the cold gas becomes stable. Or you can actually use the cold gas on a very rapid timescale so that you're left without any gas. And finally, you can physically remove the gas with outflows. So as you can see, we have plenty of choices for the mechanism that is behind quenching and that ultimately causes the existence of quiescent galaxies. there was a very popular paradigm for a long time, which we could call the major merger paradigm. It was very popular, at least in part due to this beautiful illustration from a paper by Phil Hawkins and others, where you start with a spiral, it encounters other spirals, so you have a major merger, you go through a ultra-luminous infrared galaxy phase, a blowout phase, a quasar phase, then you're left with the post-starburst system. This is a very important type of galaxy, and I will talk about this today multiple times. These are galaxies that are quiescent, they're not forming new stars, they don't have emission lines, but their stars are rather young, A-type stars, and you can see this from their spectra, meaning that they had a recent burst and then quenched rapidly. So if you go through these steps, then you basically end with a dead elliptical. And the beauty of this paradigm is that it explains two things at once. It explains why elliptical galaxies have a different morphology, that's due to the scrambling due to the major merger, and why they turned off their star formation activity, and that's due to the quasar phase. And in this particular model, you see the star formation rate and the quasar luminosities, and everything happens over a few hundred million years. It's a very rapid event. Now, like all beautiful things, this is also probably not correct. People went out and tested this paradigm, and you can measure the number of mergers in the universe, the number of post-starburst galaxies in the universe, and they don't match the rate you expect from just the number of ellipticals that we need to create. And you can also look at galaxies that are transitional, and most of the times they don't show any tidal features or any remnant of major mergers. Now, this doesn't mean that major mergers are out of the picture, as I will explain later. However, right now, the most, let's say, popular scenario, certainly among theorists, is AGN feedback, particularly heating of the gas by AGN feedback. And this is implemented in one way or another in all the major cosmological simulations, which in their latest generations are really able to reproduce galaxies, reproduce a lot of the observed properties of galaxies in an impressive way. For example, in TNG, you can explicitly see that major mergers do nothing to obtain the population of quiescent galaxies. So this is a very interesting mechanism. Unfortunately, there isn't really any direct observational evidence that connects AGN feedback to galaxy quenching. It doesn't mean that, you know, we're not going to find it one day, but at the moment, this works mainly on the theory side. So what I want to do is to just show you a few different projects I've been working on. And the main goal here is to characterize the population of massive quiescent galaxies at high redshift. We want to do this at high redshift because we want to get as close as possible to the quenching epoch. And for the most massive galaxies, this happens at high redshift. So using different telescopes and including one fun adventure in the world of simulations, I've explored different properties that you see here. And at the end, hopefully, we'll try to have a consistent picture for all of these. So let's start with the stellar kinematics of massive quiescent galaxies. Well, in the redshift 0 universe, of course, the most massive galaxies are not only passive, but also ellipticals. And this does not seem to be the case at high redshift. And this became clear for the first time about 10 years ago with the first near-infrared images from Hubble, where you can just look at the morphology of quiescent galaxies, and you see that they're elongated. They're more elongated than what you find at redshift 0. What you really want, though, is to measure the kinematics, but these galaxies are very small. So here is an example, and this is the slit on Keck that I used to take a spectrum of this galaxy. So you only get one spectroscopic measurement. You cannot spatially resolve these galaxies. But what I did was, with a sample of galaxies between redshift 1 and 2.5, was to look at the statistical effect on the population of rotational support. So the basic idea is to measure the velocity dispersion and compare that to the morphology, the axis ratio. If you find that edge-on galaxies have a higher velocity dispersion systematically compared to face-on galaxies, so rounder galaxies, that clearly means that there is rotational velocity. And you can compare that to redshift 0 measurements. And I found that there is about a ratio of 2. So at high redshift, galaxies are rotationally supported as measured by V over sigma, which is the ratio of velocity of rotational velocity to pressure support, by a factor of 2. Now, another study at redshift 0.8 was able to marginally resolve these galaxies, and you can see in black the rotation curves. And you do see some rotation. Of course, the effect of seeing is going to smear these measurements. So this is a lower limit on the rotational velocity of these systems. So what you really want to do is spatially resolve one of these or a few of these. And either you wait for the 30 and 40 meter telescopes, or as always, you go and find some gravitational lenses. Now, this is particularly difficult for quiescent galaxies because they're very rare at redshift 2. So in this work led by Drew Newman, we found only 4 systems in about 200 clusters. But these 4 are really good. They are very quiescent and very elongated. And this elongation is all due to the gravitational lensing effect. So they're also brighter, of course, because of the lensing. So this means you can put these slits on them and spatially resolve them and obtain multiple absorption line spectra. And for each spectrum, you measure the velocity, and you can build this nice rotation curve. So these data are from both Keck with the MOSFET instrument and the FIRE instrument at Magellan. And in these 4 cases, you see the velocities in blue, and we're talking about hundreds of kilometers per second in rotation. And the velocity dispersions are in red. Now, you do have to account for the lensing effect, which will distort your measurements, but you can do this and then actually get to the intrinsic kinematics. And once again, the result is pretty clear. These are extremely massive galaxies, and in the local universe, basically, they would not exist. Even rare galaxies will never show this high level of rotational support. One of these galaxies was independently discovered and followed up also by Sune Toft, and he finds completely consistent results. Now, this has an incredible implication for our quenching scenarios, because now we don't need to explain both the turning off of the star formation and the change in morphology at once, because they can happen at different times. So this original idea that we want to explain how a local spiral forms a local elliptical really doesn't work, because the progenitors of these galaxies are at high redshift, and they might be even similar. One of them maybe kept forming stars until today, and that becomes a spiral. One of them quenched and became a quiescent disk. And then you only need to explain how to form an elliptical from a disk. But this is actually the easy part, because we already know that once galaxies become massive and quiescent, their history is dominated by dry minor mergers, which means they accrete other gas-poor satellites. And this explains why quiescent galaxies are very small at high redshift and very large at low redshift, because they're accreting these satellites, and their stars go preferentially to the outer parts of the galaxy. But this accretion also will disrupt the angular momentum, and therefore explains very naturally how to go from a disk to an elliptical. So the next step is to study the stellar ages of these massive quiescent galaxies. And I've done this also with Keck spectroscopy. So this is a rather large sample. I'm showing here only the redshift 2 galaxies. We also have redshift 1 and 1.5 galaxies. And with these Keck spectra shown here on the left, we can fit models, such as this one's in red. We also model the photometry at the same time. And we can get out the star formation histories, which are shown here in the panel on the right. So these are basically the distribution of the ages of the stars in these galaxies as a function of look-back time. I will talk about how to do this in detail later on, because this is really an important aspect of studying galaxies that are quiescent. And here I've sorted them by age. You can measure the median age of each of these galaxies just to have a number. And you can see that some of these are very young, less than 1 gigayear, and we can call these the post-starburst galaxies. Some of them are intermediate ages, and some of them are old. Now, everything is relative. Of course, they can be older than 3 gigayears, which is the age of the universe at redshift 2. And if you know anything about this type of spectra, you'll see by eye that these ages sort of make sense, because you see for post-starburst galaxies, these very deep absorption lines. And for older systems, the calcium lines being stronger. So what I've done then is I've plotted the age of each of these quiescent galaxies on their position on this UVJ diagram that we saw earlier. Now we're focusing only on the quiescent part. The star-forming population lives here, and we didn't observe them with KEC. And you see by eye that if you only consider galaxies beyond this black line, there is a very clear trend of older galaxies with redder colors. This may seem natural, but actually there is also the effect of dust baked in this relation. So this is not something you can come up just using models. You really need to observe these galaxies, take deep spectra, and then measure their ages. And now what we can do is to come up with a very simple fit that tells us the age of a galaxy starting from their colors. So this is a linear fit. And if you apply that to this galaxy, you will get these sort of colors or ages, which look very similar to the measured ones. So the linear fit is a good approximation. And this means that now we can infer, we call these the inferred ages. We can infer the ages from the colors of a large sample of galaxies without having to take spectra, which are extremely expensive at this redshift. So we take the UltraVista survey, which is a volume-limited large survey, photometric survey. And for each quiescent galaxy, we just infer the age according to this simple formula. And here you have a population of galaxies that will have inferred ages that are quite young, less than a giga-year, and we call those the post-starburst galaxies. And so I select post-starburst galaxies here with this blue box. And now the question is, do all galaxies evolve along this sequence? So they first become post-starburst, and then as they age, they move along this red sequence. And the importance of this question will become clear later. But now we can actually test this question. So what we do is we split this large sample in redshift bins, and we choose the edge for each of the edges of these redshift bins accurately, so that each of these 4 bins have the same cosmic volumes. So you can interpret these plots as a number density. So you see quiescent galaxies are very rare at redshift 2.5, and they become very common at redshift 1. So you are seeing the growth of the quiescent population. And now the question is this growth consistent with galaxies always going through this blue box? So being post-starburst for just a short amount of time and then becoming old. And we can test this because we know the ages of each of these galaxies. So just as an example to explain this, this is as if we were trying to study the population in a certain city. So let's say in the year 2000, we take census, we count the people in this city. It's a small town, we only find 7 people, 3 of which are children. So these are the young people, so they're post-starburst. And now we try to predict the population after 20 years. And we know that these children will grow up and become adults. So we'll have 4 + 3, 7 adults, and new children, maybe another 3, so about 10 people. Now you wait until 2020, you take the census, and then now you count maybe 16 people. This means that 6 adults came into the city as adults. They didn't grow up there, right? And this is exactly what happens for quiescent galaxies. The observed growth rate here in red of the overall quiescent population is too high to be explained with the growth rate due to only post-starburst galaxies. And the discrepancy is a factor of 7 at the lower redshift end and a factor of 2 at the higher redshift end. The conclusion is that not all quiescent galaxies became post-starburst at some point in time. This is not a step that every galaxy has to go through. And galaxies must therefore cross this diagonal line on the UVJ diagram. So what does that mean? Well, you can actually use very simple toy models where if you take a star-forming galaxy and you calculate the colors, and then you quench very rapidly the star formation, for example, using a 100 million year timescale. And in this case, you have this blue path that goes through the post-starburst blocks. But if now you set the quenching timescale to 1 giga-year, you obtain the green curve, and now you're crossing through this diagonal line. So this is evidence for two quenching paths at the same redshift. So they're simultaneous. It's not something like the quenching timescale is evolving with redshift. They both happen at the same redshift, but with different contribution. So we need both fast and slow quenching. Now, of course, it doesn't mean it's exactly two. It could be a continuum of timescales. Now, what happens if we go to even higher redshift? Well, if we extrapolate our plot here, eventually, should these two curves meet so that at redshift 3, say, the post-starburst growth, the growth due to post-starburst actually is enough to explain the overall population? Well, actually, the answer is yes, because recent observations found quiescent galaxies at redshift 3 and even 4. And if you put them on the UVJ diagram, as they did in this recent paper, you'll find that basically all of them are either in this post-starburst box, or they're even bluer, so they're even at the earlier phases of the post-starburst evolution. So I think this is really an important point. And when we talk about quenching, there probably is more than one way to quench. And so where do we go from here? Well, every time you have to draw these arbitrary boxes on color diagrams, you know, there's room for improvement. So what we're doing is to try and forward modeling the overall population on the UVJ diagram. And this is a project that I've done with Sandro Tacchella and Joel Leja with a summer student, Leah Zuckerman, who is an undergrad at Brown and was part of the RU program here at the CFA this summer. So what we did was using a set of stochastic star formation histories that Sandro developed, where we are describing a star-forming galaxy just as a random process that go up and down around a certain level. And then we use the flexible stellar population synthesis library written by Charlie Conroy. And we make synthetic galaxies. We measure their synthetic colors. And then we plot them here. This is a track of a galaxy. You can't see it, but it's oscillating because of these star formation histories. They have some stochasticity in them. So it will go a little bluer, a little redder, a little bluer, a little redder. And then you have to pick a value for the stellar metallicity, and you have to pick a value for the dust attenuation. And you can do this for thousands and thousands of galaxies. And once you do that, you obtain a population of synthetic galaxies. And you compare that to these blue points, which are the observed galaxies. And what Leah found is that you can actually reproduce the star-forming population remarkably well with an extremely simple model where the dust of each galaxy is really randomly drawn from a uniform distribution. And this is quite, I felt a bit uncomfortable when we discovered this, because we even tried to have more physically reasonable models where the dust attenuation follows, for example, the star formation rate. But they don't reproduce as well the observed colors. And we interpret this as being evidence for the extreme importance of viewing angle. So the dust attenuation here is completely random. This must mean that it's only due to the fact that we're seeing some galaxies mainly edge on and some galaxies face on, and the amount of dust will vary a lot. So unfortunately, this means that these colors don't tell you a lot about the intrinsic properties of galaxies. But if you can reproduce the star-forming population, that means now we can start investigating the quiescent one. And now we are introducing quenching in these models in a very simple way. This is what we find. And as you can see, by trying to match the models to the observations, we may be able to find a way to constrain the quenching timescale or the distribution of quenching timescales. So let's now talk about a different aspect, which is the size of these, particularly of these post-starburst galaxies. Now, a very important property of post-starburst galaxies is that they are compact. They are much more compact than regular quiescent galaxies. This is the mass-size relation. Regular quiescent galaxies are here, and these stars represent post-starburst galaxies. So at the fixed stellar mass, they have about half the size. And this is often interpreted as being consistent with a scenario sometimes called compaction, where we have gas-rich events such as major mergers or even counter-rotating streams that lead to a loss of angular momentum. So the gas collapses at the center and forms new stars. So you end up with a very compact system. And this could explain quenching for these post-starburst galaxies. And in some sense, I like to think of this as a comeback of the major merger paradigm, because the basic idea is very similar. You need like a very dramatic event, mainly due to major merger, with one important difference, which is that at high redshift, the gas fractions are much higher. So you actually don't necessarily need a major merger. You could have these, again, with streams that are counter-rotating, so you have a dissipational event. And also, because of these high gas fractions, you end up with a very compact remnant. So if this is true, this would have important implications for our understanding of quenching, particularly for the rapid quenching. So over this summer, I worked with a different undergrad, Bimodality Patak from Grinnell. She was part of the Banneker Institute. And together with Rainer Weinberger, who is part of the TNG team, we looked at post-starburst galaxies at redshift 2 in the TNG simulation. And we really explicitly looked at the sizes of these galaxies. So here is the selection of these galaxies. You're looking at star formation histories. So these are all the post-starburst galaxies, and the median is in black. And by construction, these galaxies are starting off slowly, then they have a burst, and then they have a rapid quenching. And we also have control samples of intermediate age quiescent galaxies and old age quiescent galaxies at the same redshift and in the same mass range. So we now measure the sizes of these galaxies, and we plot them here. This is again the size versus mass plot. And now the black points are post-starburst galaxies, and they actually are larger than all the other quiescent galaxies. So in TNG, we find exactly the opposite trend, where post-starburst galaxies are larger. This is a huge contradiction with observations. But there is a catch, which is that we are looking at the size as defined by the half mass radius, because this is a simulation. We don't work with light, we work with actual particles with some mass. Whereas observations look at the light, the half-light radius. And while we were doing this project this summer, two really interesting papers came out from two different teams. In this first one, they studied not only the half-light radius of observed galaxies, but they tried to measure the half-mass radius. And as you can see now, these post-starburst galaxies are going up. That means that they appear more compact than what they really are, because probably they have younger stars that are brighter in the center. And in a different paper, this one is at lower redshift, about 0.8, where it's almost possible to, it's possible to spatially resolve these post-starburst galaxies. They took a measurement of H delta, which is an absorption, a Baldwin absorption line. And when it's higher, so it's a stronger absorption, you have a younger stellar population. And the post-starburst galaxies, which are in cyan, show a clear trend where in the center they have stronger H delta. So again, this confirms that in the center they are brighter and have younger stars. And so we went to our TNG galaxies and we looked for the age profile. Now, of course, in the simulations, you can do this with an exquisite level of detail. And our post-starburst galaxies are shown in the first panel. This is the median age as a function of position along the galaxy from the center to the outskirts. And you see a clear positive trend, which is the opposite of what we find for older galaxies. Older galaxies have the typical trend, a typical profile with younger stars in the outskirts. But post-starburst galaxies show the inverse of that, with younger stars in the center. So even though the TNG simulation is not able to capture the size of these galaxies, it is definitely able to capture the age profile, the fact that qualitatively, these are very different galaxies. And it is consistent with the fact that they formed and they quenched with dissipational events. And you can go in more detail and look at the distribution of the stellar particles for each galaxy in the simulations. So these are two post-starburst galaxies as an example. And each point now is a stellar particle. And we're looking at the stellar ages as a function of the distance from the center. So this black line would be one of these black lines here. And when you look at the particle data, you immediately see that this trend is not due to a smooth distribution of stars, but you see these clumps, which are starburst events that are very narrow in age. So they're very rapid, and they happen preferentially in the center. This one is a major one. Here you have multiple smaller ones, and we find these in many of these galaxies. So we are now in the process of looking at the merger history to really pinpoint whether this was due to major mergers or accretion. But clearly, we find that even in the TNG simulations, where quenching by construction is due to a strong AGN feedback, we have a population of galaxies that undergo rapid quenching at high redshift. And this is due to dissipational events, likely. For the last part of my talk, I want to talk about gas now, particularly the molecular gas. And now this is a very important ingredient that we need to study for understanding galaxy quenching. And the reason is that different quenching mechanisms actually have different predictions for the molecular gas, for the gas reservoir. So what we want to do is to measure this depletion time for quiescent galaxies and compare that to star-forming galaxies to see if the efficiency of star formation is intrinsically different or not. This is a very difficult project. I've been doing this with my colleagues at the Max Planck Institute for Extraterrestrial Physics. And we have a very small sample of only 3 galaxies at redshift 1, but we detect all of them in CO. And we used NOEMA to observe the CO emission line. Now, the way we did this was to first select galaxies from a Keck sample that I've already talked about. These are ratios between 1 and 1.5. And out of these galaxies, I picked 3 which are bright at 24 micron. This is based on recent results that show that you're more likely to have a CO detection if you are a little brighter at 24 micron. So something to keep in mind is that these are not 3 randomly drawn quiescent galaxies. It's a biased sample. But the reason is that people tried before to pick random, truly quiescent galaxies, and even with ALMA, they couldn't detect CO. It appears that these really have very low levels of gas. So we have Keck spectroscopy on one hand to study the stellar populations, and NOEMA spectroscopy to study the molecular gas. So what do we do with this data? Well, start with the stellar populations. So what we do is actually using this code, which is called Prospector and was developed here at the CFA by Ben Johnson and Joel Leja. And this is really the ultimate code for fitting spectroscopy and photometry. It's a fully Bayesian inference code, which is extremely flexible. So here you're seeing, for one example, the photometry in blue, including the 24 micron detection, and the spectroscopy in blue on this panel with all these Balmer absorption lines, some oxygen to emission here. And the red line is the same best fit model in both panels. So we're fitting simultaneously spectrum and photometry. This is very important because the spectroscopy only spans a narrow wavelength range. So it doesn't tell you, for example, a lot about dust reddening. Now, we do this using a 20 parameter model to describe each galaxy. So it takes about 2 days to run for one galaxy. And at the end, you're left with these 20 posterior distributions, one for each parameter. So what are these parameters? Well, you have the usual redshift, stellar mass, and so on. And then we have 8 independent beams for the star formation history. So we don't assume an exponentially declining or any other parametric form for the star formation history. Then we have 3 parameters for the dust attenuation and 3 parameters for the dust emission. And these are self-consistent so that the energy that is absorbed by dust is then re-emitted. And then we also have nuisance parameters to deal with the fact that the spectra often have outlier pixels and the uncertainties aren't well calibrated. So now I'm going to go through the sample of 3 galaxies one by one, and I'll show all the data we have. So these are all in the Kendall's field. So we start with really great imaging from Hubble, multiband imaging. And this first galaxy is already very interesting when you look at the imaging. It is a remarkably large disk for this redshift. It's a redshift 1. And it has a smooth profile in the near infrared, but clearly a clump in the restream UV. And the NOEMA spectrum shows, intriguingly, 2 peaks, of which one matches the redshift from the optical spectroscopy. And the other one, which is the blue peak, is marginally spatially resolved and appear to be really coincident with this clump. And because these 2 peaks are 500 kilometers per second apart, it's unlikely that this is just a rotating disk. It's more likely that we are looking at the emission from 2 different systems, basically. One is either the bulge or the disk of the galaxy, and the other one is this clump, which now, being at 500 kilometers per second away, it really isn't a clump. It's more like a minor merger. It's an accreted galaxy. And we have the spectrum for this galaxy, so we fit it together with the photometry, and we obtain the star formation history. So this is the star formation rate as a function of look-back time. And we see at very high redshift, the galaxy was highly star-forming, and then it declined slowly until very recently, when the star formation rate increased from 10 to 20 solar masses per year. And it's really amazing that we find this consistent picture where from the spectroscopy, we recover that something happened recently, and this certainly has something to do with this satellite. So I'm gonna call this the rejuvenated galaxy. The second galaxy is interesting in its own way. It has a messy UV morphology and a tidal tail, so maybe it's a post-merger system. It has a fairly low signal to noise CO emission, which shows an offset with the Hubble imaging. We don't know if it's real or due to the poor signal to noise ratio. These data, actually, we didn't take them. They are from they're archival data because this galaxy was observed by FIBS, and they're public already, so they're shallower. These previous ones were more than 10 hours on source with the upgraded NOEMA array. Now there are 10 antennas on NOEMA, so it's really quite sensitive. And here the star formation history is really similar to the first system, but we don't see any meaningful rejuvenation. And there is no sign of merger, maybe because of the signal to noise ratio. So we call this simply the slow quenching system because it shows really a slow decline of the star formation rate. And the final system is very compact, very narrow CO emission. And clearly, this is a post-Harbor system. Look at these Balmer absorption lines, and these fall off in the last 500 million years from the star formation, star formation history. So that's the post-starburst. And now we can measure the CO fluxes and convert them to measure the mass of the total molecular gas in the galaxy. And we put it in context. So this is the gas mass divided by stellar mass. So it's a fraction of mass in gas as a function of redshift. And these are all star-forming galaxies. So clearly there is an evolution. It's a well-known fact. At high redshift, there is more gas. Now for quiescent galaxies, at low redshift, they have 2 to 3 orders of magnitude less gas than star-forming galaxies. And there are some measurements at redshift 0.7, including for 2 post-starburst galaxies shown in green. But above redshift 1, we only have basically non-detections from the literature. But now we can add our 3 points, and they are all below the known star-forming galaxies at that redshift, which makes sense. These are quiescent galaxies, and so they have less gas. But what we really want to look at is at the depletion time. So that's basically calculated as the ratio between the star formation rate and the gas mass. And now on these plots, you see that all of those galaxies that were at different redshifts and different gas masses and different properties, they lie almost on a constant depletion timescale. So the depletion time varies only by a factor of 2 over this redshift range. And it appears that all the star-forming galaxies and the quiescent galaxies have the same depletion time of 1 giga-year. So that would be quite interesting. However, one really big problem with this plot is that I measured the star formation rate for all galaxies here from the sum of the ultraviolet and the infrared light. And this works well for star-forming galaxies. But for quiescent galaxies, there are a lot of studies recently that have shown how this systematically will overestimate the star formation rate, because the infrared is much brighter than what you would expect due to the contribution of older stars. Older stars will also hit the dust, and then this will re-emit in the infrared. So we need a different method to calculate the star formation rate. Well, we have these beautiful fits to the spectrum and the photometry. If we take just the last bin of the star formation history, that's the star formation rate average over the last 30 million years. Now, we cannot do that, unfortunately, for the star-forming galaxies, particularly at high-redshift, because we don't have the spectrum. But if we do that for our points and for the points from the literature at redshift 0.7, now we have a very different picture, where these red points that are truly quiescent and our slow quenching point have a longer depletion timescale. And the post-starburst galaxies and the rejuvenated galaxy have a 1 gigayear depletion timescale. And there is yet another way you can use to measure the star formation rate. As you saw, the oxygen 2 emission line is often detected in these systems. So you can correct that flux for dust attenuation using the results of the spectral fitting, and then convert this intrinsic O2 emission line flux to a measure of star formation rate using local calibrations. And if you do that, now all quiescent galaxies have a depletion time of about 10 gigayear. So as you can see, there's a huge range of star formation rates that you get if you use different methods. And this has important implications for the results. So for my 3 galaxies, if I use the UV plus IR method or the oxygen 2 method, I get a difference that is an order of magnitude in the star formation rate and therefore in the depletion time. Now, I believe that the oxygen 2 line is probably affected by the geometry of dust attenuation. So from the spectral fitting, we get the overall dust, but we don't know exactly where the oxygen 2 is coming from. If it comes from really the most dust obscured regions of the galaxy, then you will definitely get a lower star formation rate. So I believe that for this particular sample, the spectral fit gives the least biased measurement. So if we believe this result, it seems that post-starburst galaxies, unlike older quiescent galaxies, seem to have normal depletion time. And this is very interesting because it means that quenching in these systems can simply happen because you either use up all the gas or you remove the gas. You don't need to come up with any special way to change the efficiency of the transformation of cold gas into new stars. So let's try and put all of this together. Here is a very tentative scenario for how massive quiescent galaxies form. So at high redshift, we have highly star-forming galaxies that are the progenitors of local large ellipticals. And one way to do this transformation is through slow quenching. And this could be due to the heating of the gas from AGN feedback as implemented in cosmological simulations. However, there is definitely at least another way to do this, because you need to reproduce these post-starburst galaxies that we observe. And this could be due to a fast quenching where you have gas switch events, major mergers, or minor mergers with very gas switch satellites, or very high gas fractions that lead to disk instabilities, or counter-rotating streams, and things like that. And these will form compact post-starburst galaxies. And then you need to grow these into the local large ellipticals, and we do this. We now think we know that this is a pretty robust result. We have a lot of dry minor mergers on these galaxies, so that this causes two important things. It increases their sizes, and it scrambles the stellar orbits so that there is a loss of angular momentum. And that is how we finally end with the local large ellipticals. And I'm done. Thank you.
Thank you, Sirio. One of the features of Zoom that we haven't quite mastered is how to clap at this moment. So for questions, we can use the raise hands feature. So if anybody has a question for our speaker, please go and use the raise hands in the participants menu. And I'll take the first question if I may. So dust plays a role in many parts of the story, but it appears that you have the least real theoretical understanding underneath this of what's going on with the dust. So what can you do about that? Are there observations that are likely to be possible, say, with JWST that will help resolve this?
So that's absolutely a good point. On the one hand, there's not much we observers can do about that. The latest cosmological simulations are really great, except in the fact that they don't have dust. You can add dust in post-processing, but it's not really part of the simulation. And when you try and also add it, the results so far haven't been really great. And of course, when we observe things, dust is the first thing you see. So this is definitely one of the major problems in comparing simulations and observations. I think that with JWST, actually, we can make a lot of progress, more in the understanding of gas in real galaxies, gas and dust. And for example, we will be able to measure more accurate star formation rates, even from the infrared, when we'll have a spectra over a wide wavelength range for these quiescent galaxies. We can then really study the emission from dust.
Okay, thank you. So I don't see a hand up, but I think Ramesh put his hand up, but maybe took it back down again. I'm not sure. Okay, well, any questions, anybody else? Okay, well, I'll try. I have a second question, so I'll take again my privileges here. So another question for you is: are you confident that the balance between molecular gas and atomic gas is understood? And if there were a lot of atomic gas, would you be able to pick it up, say, in maybe one of the carbon fine structure lines?
No, I'm not confident, and we're not gonna probably be able to pick it up in these quiescent galaxies. So we really are at the edge of what we can do just with the CO emission. Now, there's even another step, which is between CO and molecular hydrogen, which haven't really talked about. But there are a lot of leaps of faith in going from observing one CO line to interpreting all of these about the state of the gas in these galaxies. But we really are limited by observational capabilities at this moment because the gas fractions are so low in these quiescent systems that it's really challenging to study them in detail.
Well, while we're talking about gas fractions, I mean, you do have local elliptical galaxies, and the gas fractions are really quite low in many of those, isn't that right? They're very, very small.
Yeah, they are extremely small, like less than 0.1% sometimes. Of course, high-redshift quiescent galaxies aren't quite the same type of galaxies. Mm-hmm. So we hope that there's more gas and dust there.
Charles, I haven't seen, but I did have a question myself.
Go ahead.
Sirio, you mentioned at the beginning of the talk that the observations show that the largest, most massive galaxies formed early, whereas the hierarchical models would have assumed that they would form late. It didn't seem like this this solution addresses any of that question of where did the very largest and why did they all form early, or did I miss? Is there some other conclusion that I missed?
Right. Yeah, I didn't address that explicitly. This is one of the main results of the last 10 or 15 years from the theoretical point of view. It was clear that by adding in a quenching mechanism on top of lambda CDM, then you could definitely reproduce this, simply because the more massive galaxies start growing a lot, but when they reach a certain stellar mass, they stop growing. So in lambda CDM, naively, those galaxies would keep growing until today, and then you would have a 10 to the 13 or 10 to the 14 solar mass galaxy, which we don't observe.
I see. So you have now two different types of quenching, but both have the same effect.
Pretty much.
Okay.
Okay. So I'm wondering if there's something a little bit flaky about our hands raised feature, because I think I saw both Tony Stark and Rainer Weinberger raise their hands and then go down. So if either of those actually has a question, maybe just speak up. Tony.
Oh, yes, I guess my question is, to what extent is all of this modified by the density of clusters, in other words, the environment that the forming galaxy is in?
Yeah, so the environment is a very important aspect, which I didn't touch on. The environment is really critical for satellite galaxies. So we don't only, of course, want to reproduce massive galaxies, we also want to understand and reproduce in the models lower mass galaxies. And for those, if you don't include the environment, you'll never obtain quenching, in the right way. So for lower mass galaxies, the environment is critical. For high mass galaxies, depend what we mean by environment. All of these are in extremely dense environment at redshift 2 or 3 or 4, because they're the most massive galaxies in the universe. So in some sense, I'm not talking about it because I don't think it makes a difference from one galaxy to another. But definitely, if you didn't have such a dense environment, you couldn't have this high accretion that you need to form these massive galaxies, and also high density of massive galaxies that you need to perhaps have for major merger and compaction and all of that.
Okay, thank you. So Igor has a question. You can speak up for yourself if you want, Igor, or I could read it out for you.
Okay, I'll speak it. Yes. So, hi, Sirio. So I have a question regarding some of the quenching mechanism that you haven't mentioned. It's RAM pressure stripping. So we know from simulations and actually from observations now as well that RAM pressure can produce starburst. It can induce starburst by gas compression, and so it would end up with RAM pressure with PSGs, with post-starbursts, mostly in the lower mass end in clusters. So how important is this mechanism? Because it's not on your diagram at all.
That's right. It's not on the diagram because the diagram is only for central galaxies and RAM pressure stripping.
Ah, okay.
For satellites. So as I said before, I would consider that environmental quenching, which applies to satellite. And it is extremely important, but it's not an effect that we need to worry about for massive centrals.
Okay, so I think we have addressed all of the questions that have been raised so far. So with that in mind,
Charles, may I ask a second question?
Go for it.
Okay, quite a long time ago, I had a paper on post-starburst galaxies done with VMOS, and those were relatively nearby. So those came from a sample of massive post-starbursts with H1 detections. Could you comment on how is this in general possible when you have no star formation, no presence of emission lines in the optical, but you do have presumably large H1 reservoirs?
Yes, excellent point. So part of the motivation for the last study I showed about the molecular gas in post-starburst galaxies actually come from lower redshift studies that sometimes are finding elevated gas fractions in post-starburst galaxies. Sometimes they find that the CO emission is way above what you would expect, given the star formation rate you measure. And this is absolutely an open question. There are two main explanations. One is that we are actually looking at an extremely dust-obscured system, and so the problem is in the measuring of the star formation rate. We think it's quiescent, but really there's a lot going on there behind a dust screen. And the other explanation is that you actually, because of mergers or other dynamical effects, you achieve something sometimes called morphological quenching, which means that the cold gas can be kept stable against collapse, and so it won't form stars. But I think that's absolutely an open question.
Okay, I think we may actually have reached a natural conclusion to this Clay lecture. I'd like to thank speaker Sirio once again for a very illuminating talk, and I wish you all the luck in the world learning more and more about these interesting systems. I'd like to thank Thomas Clay for joining us from Colorado, and thank everybody else for helping to make this a success.